as we saw in the Atoms in Motion app, the atoms, or particles, a word we'll often use, of a substance are in constant random motion. So this means they'll all be going in different directions with different speeds. Now that's kind of clearest to see for a gas. For a liquid, they're kind of close together but still moving about randomly, and for a solid, they're fixed in place overall, but they'll vibrate in place. But we still have this idea of constant random motion. And that then gives us a definition of temperature. So the temperature of a substance is a measure of their average or mean kinetic energy. So some are going faster than others, but if you knew their average, then that would give you an idea of temperature. That's how temperature is defined. Which means if you heat something up, i.e. add more heat in general, then temperature is going to rise, which leads to our next learning outcome. So temperature is all about the individual energy, individual particles, and their energy, whereas heat is about the total energy in a system. Okay, so when we add heat energy to a system, and by system we just mean something like a sample of gas or something like that. So the total energy in the system increases. And that can only happen if the individual energy increases. On average. So the energy of the individual particles increases, i.e. that's what we just defined temperature to be. So i.e. supplying heat can cause temperature to increase. The opposite is also true. You remove heat from a system, you slow them down. Right, the total energy decreases, the energy of the individual ones decreases as well. And it's not the only thing that can happen when you add energy. We'll come back. We saw in the first experiment that we did that when you heat water, first of all its temperature goes up, but then obviously you reach its boiling point and we start to look at changes in state, but we'll come back to that in later learning outcomes. And that leads us into a definition of specific heat capacity. So specific heat capacity is the amount of heat energy, so we're back to talking about total energy, required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So it's giving you the energy per kilogram per degree Celsius. And that then leads to a formula. I'm going to put that on the next page. So with that definition, if C, which is a letter for specific heat capacity, is the energy for 1 kilogram and 1 degree Celsius, right, a change in temperature of 1 degree Celsius, well, if we multiply it by whatever mass we've got present, so if you had 3 kilograms, you need to multiply it by 3, and multiply it by what change in temperature, so that's delta symbol, the Greek letter, capital delta, and it means a change in something. So delta T means change in temperature. So from that definition of C, this formula just kind of comes from that, right? Because C is the heat energy needed for 1 kilogram and a change of 1 degree Celsius. So you multiply by how many kilograms and how many degrees Celsius you want it to change by, you'll get how much heat energy is required in general. So as usual, we'll define all the symbols and their units. And basically, specific heat capacity then you'll find in tables in the data sheet. So it's been measured accurately. You're going to do experiments to measure it as well. Its units are joules per kilogram per degree Celsius, or as we'll sometimes see it written per Kelvin, but we'll come back to Kelvin units for temperature later. And it's been measured, so you'll find it in data sheets. You can just look it up, and there's specific values for each material. Fairly obviously the mass, don't forget it should be in kilograms. I know a lot of chemistry work you do is in grams, but the standard unit of mass in physics is the kilogram. And delta T, so the delta bit means change in, and the capital T stands for temperature. So remember, we've got to be careful, but small t for time, capital T for temperature. And that can be measured in degrees Celsius, or I'll stick the K in just now for Kelvin, but we'll cover that in the next chapter. So, a couple of examples. Calculate the heat energy required to boil a kettle of water with 1.5 kilograms of water at 20 degrees Celsius, a kind of normal room temperature. Water has this property, you may have come across that 1 kilogram of water is 1 litre of water as well. So just if you ever come across anything in litres, it's just the same in kilograms, but it should really be in kilograms for you. So if we write down what we know, we've got a mass. Now we've got a starting temperature, so I'm going to call that Ti for initial temperature. That appears to be all that we're given in the question. So we've got to read about a wee bit more. And we're talking about boiling the kettle of water. So that tells us that T final is 100 degrees Celsius. So putting those two bits together, we can get that delta T is 80 degrees Celsius. And the value of C, let's say, is given in data sheets. So you can look it up and we can find that C for water is 4,180. So now we can do our formula. Should have listed, of course, what are we being asked. And the equation that links all these together then is EH equals Cm delta T. So it's 4,180 times 1.5 times 80. Stick that in the calculator. It's 501,600 joules. Heat energies usually are quite large. It takes quite a lot of energy to heat things. And I did mention the other day in class this idea that actually water is quite good for storing heat energy. So we tend to get quite large numbers because the specific heat capacity is large. We'll do one more example. This is where we're reorganising the formula. So we're going to look at an experiment to measure C So find that it takes 24,500 joules to heat 0.5 kilograms of aluminium by 50 degrees Celsius. Calculate C. And compare to the accepted value. Come back to that accepted value in a wee second. So what we're told in this question is EH and we've got the mass 0.5 kilograms. We're not given a starting temperature and a final temperature, but we are just told that it went up by 50 degrees Celsius, so we can just go straight to delta T. We've been asked to calculate C. So, usual formula, linking them together again. Remember, write out the formula as it's given. Plug in the values that you know. And then how we're going to rearrange to get C. Well, what I would say with this formula, because there's 4 bits in it, is first of all, simplify what you can. So, just realised I wrote the wrong number there. It's 24,000. So, 24,500 equals C, but we can do the 0.5 times 50 bit and get 25. Swap sides. Get C onto the left hand side, but I'm not changing anything. But now to get C on its own, I'm going to divide both sides by 25. That cancels out on the left hand side, times 25 divided by 25. And the calculation, we get 980 joules per kilogram per degree Celsius. The second part of the question asks us to compare to the accepted value, and this is quite common in the way these questions are phrased. So the accepted value, if you look up the data, for aluminium is 900 joules per kilogram per degree Celsius. So measured value is larger, and if you were asked to comment on that, this is quite common that we find the measured values are larger than we'd expect. And the basic reason is that when you're heating up that block to measure the change in temperature, as soon as it's hotter than the air around about it, it's going to start losing heat to the air, which means that heat's not going to stay in the block and keep it as warm. So you can obviously try and minimise that effect by insulating the block, but you'll never solve it perfectly. So the measured value is larger because heat gets lost, or heat is lost to the surroundings. That's quite a common phrase that will come across in these heat experiments. So when you perform these experiments, you'll probably find that your values are higher, and often even quite a bit higher than the accepted values.